Let's continue our discussion on the p-n junction at thermal equilibrium. We will focus on the band diagram and how to determine some important parameters used to characterize the depletion region. So what are learning objectives of this video? After this video, you should know what a band diagram of a p-n junction at thermal equilibrium looks like. Once that picture is clear in your mind, I will explain how to calculate the intensity of electric field in the depletion region. Finally, we will use that calculation to determine the width of the depletion region. These are the band diagrams of isolated p-type and n-type semiconductor materials. We see that the Fermi level is close to the valence band in the p-type semiconductor and close to the conduction band in the n-type semiconductor. Like I said before, in the p-type semiconductor material, holes are the majority carriers and their concentration approximates to the acceptor concentration. The concentration of minority carriers, in this case electrons, is calculated by dividing the square of the intrinsic carrier concentration by the acceptor concentration. In the n-type semiconductor material, electrons are the majority carriers, and their concentration approximates to the donor concentration. The minority carrier concentration is calculated from this equation. So we see that in p-type semiconductor, there are a lot of holes in the valence band, and in n-type and in n-type semiconductor, there are a lot of electrons in the conduction band. The concentration of majority carriers determines the position of the Fermi level in the band diagram. Now, let's put these two materials together to form the p-n junction. You may think that we could draw the band diagram of the p-n junction just like this, but this is not the case. As I said in the previous video, the concentration gradients of the charge carriers cause holes to diffuse from the p-type semiconductor material to the n-type semiconductor. And electrons will diffuse from the n-type semiconductor to the p-type semiconductor material. You can also remember that as the mobile charges start to diffuse, they leave behind the fixed ionized dopant atoms. The depletion region starts to be formed, and the net charge of the ionized dopant atoms builds up there. This build-up of electrostatic charge induces an internal electric field. The electric field acts with force on the charge carriers. In general, the existence of an electric field is expressed in band diagrams by a slope in the band edges. You can see in this figure that we draw a slope in the valence and conduction band edges to indicate electric field in the depletion region. So how far does the bending in the band diagram edges go? What will the final slope look like at thermal equilibrium? In order to answer that question, let's think of our semiconductor device in terms of something a bit more familiar. When we put the p-type semiconductor in contact with the n-type semiconductor, you can imagine it like having two vessels that are filled with different volume of water. In this picture, we visualize it by putting water at different levels. When we remove the barrier between the two vessels, the water level will eventually be the same in the vessel. What does that have to do with our p-n junction? The water level in the vessel is like the Fermi level in semiconductor materials. So let's go back to our band diagram of the p-n junction. the average energy of electrons throughout the p-n junction has to be the same in thermal equilibrium, like the water level in a vessel. This is shown by the fact that the Fermi level is flat throughout the whole device. We had to bend the conduction and valence bands to the point where the Fermi level of p-type region and the Fermi level of the n-type region matched up. The depletion region or space charge region is the region of the band diagram where there is a slope in the band edges. Outside the depletion region, there is almost no electric field, and these regions are called quasi-neutral regions. You can tell that these regions have no electric field because the conduction and valence bands are completely flat. So now you have a good sense of what the band diagram looks like in a p-n junction. Our next learning objective is to calculate the width of the depletion region. This may not seem to be straightforward upon viewing the rest of this video for the first time, but it will all make sense when we get to the end. When there is a net charge present in the depletion region, there must be an electrostatic potential difference between the edges of the depletion region. We call this electrostatic potential difference built-in voltage of a p-n junction. This built-in voltage is clearly visible in the band diagram of the junction, where there is a difference between the position of the energy levels of the conduction and valence band edges at the opposite sides of the p-n junction. We have to make a clear distinction between the electrostatic energy of the electrons and the total energy of electrons. Please note that in thermal equilibrium, the total energy of electrons that is expressed by the Fermi level is the same both in the p-type and n-type regions of the p-n junction. We can calculate the electrostatic energy of electrons corresponding to the built-in voltage using the following equation. This energy is obtained by subtracting the distance of the Fermi level from the valence band edge in the p-type and the distance of the Fermi level from the conduction band edge in the n-type quasi-neutral regions from the band gap energy of semiconductor. I showed you in the video on doping how to calculate the position of the Fermi levels of doped materials from the band gap. When applying these equations, we can derive this expression to calculate the electrostatic energy of electrons corresponding to the built-in voltage. A full derivation for this equation is given in section 8.1.2 of the solar energy textbook. What are important points to notice in the equation? You see that the concentrations of dopants appear in the equation. So the magnitude of the built-in voltage depends on the doping concentrations in both the p and n-type materials of the p-n junction. This is one way how to calculate the built-in voltage in a p-n junction. Another way is to apply semiconductor equations to a p-n junction. When using this approach, we start with the space charge in the depletion region.